So, so this is particle kinematics. Number 4. And you have 2 points. So this is the basket. And this is where the ball is shot from. And you know that this distance is 15 feet. And this height is 10 feet. It gives you that in meters. 3.05 meters. This is 15 feet. I guess right away we know we're going to convert that to meters to match the other stuff. 3.281 feet is 1 meter. So this is 4.57 meters. And here's what you know about the shot. You know that it is shot at an angle of 60 degrees and a speed of 7.8 meters per second. And you're trying to get it to land, basically you're trying to get it to this point to make it into the basket. Okay, so it's shot at an angle like this of 60 degrees, and it has a speed of 7.8 meters per second, and the path is going to be something like that. And we want to figure out this, the height that it's shot from. Okay, so I'm going to put my coordinate system on the ground underneath where it's shot from. And my time equals 0 is going to be the instant it's released. And time final is going to be when it, the instant that it reaches the basket. We don't know how long it takes to get to the basket. We know the acceleration because it's free fall. The initial position, well, we know that x is equal to 0, but we don't know y. We're looking for y. So I'm going to write p I x is 0, and then what we're looking for is p I y. And then the final position, well, we know what that is going to be. So PF is 4.57 for X and 3.05 for Y. Initial velocity is 7.8 times cosine and sine of 60. So I know that the x component is going to be 3.9. And the y component is 6.76. And we don't know anything about the final velocity. All right, so if you look through all the equations, there's no equation that lets us calculate PIY directly. So, no equation. That means that first we want to find TF. And to find TF, we're pretty used to using the y component equation, the PF equation. PFY is equal to PIY, that thing. But in this case, actually, that one won't work, but the x equation will. So we're going to use PFX is equal to PIX plus VIXTF plus 1/2 AX TF squared. And this says 4.57 is equal to 0 plus 3.9 TF plus, what's the x component of the acceleration? 0. Yep, so this all goes away. And so divide both sides by 3.9. And you get that time final is 1.17 seconds. And now that we have that, we can use the y equation. So this says 3.05 is equal to the thing we're trying to calculate, plus 6.76 times 1.17. Half of negative 9.81 is minus 4.905 times TF squared. We know TF. TF is 1.17. And so we have 3.05 is equal to PIY. These two together come out to be plus 1.09. And so now you can subtract 1.09 from both sides, and you get that PIY is 1.96 meters. Okay, so that is the height that the ball is released from. And okay, now we want to calculate the displacement vector from where the ball is released to where it is at the highest point. Well, remember that the displacement vector is the later position minus the earlier position. Well, now we know the earlier position. This is when what it's released from. So this is just the PI from this part of the problem. So that is 0, 1.96. But this is the position when it reaches the highest point, and we don't know that. So we're going to have to calculate those two components. Okay. So in order to do that, we have to choose a new instant to be our time final. We can still use when it's released to be our time 0, but our time final is now going to be when it reaches the highest point. Which means that any of our final stuff that we knew here, like our position final, this is all changed now. We're talking about a totally different instant. Okay? I'm going to keep the same coordinate system. Do we know how long it takes for the ball to get to the highest point? We know how long it takes to get to the basket, but we don't know how long it takes to get to the highest point. That's a little before it gets to the basket. So time final, I'm going to leave off. The acceleration is still 0, negative 9.81. The initial position we still know because we didn't change the meaning of time equals 0. So this is 0, 1.96. Final position, that's what we're trying to calculate. And we want both of these. I'll just put them both down and we'll think about which ones we can get first and stuff like that. Initial velocity is the same as it was before, 3.90, 6.76. And now the one that you've been waiting this whole time to say, I think this is probably why you brought it up, just so you could tell me what we know about V final. So if it's reaching the highest point, what do we know about that velocity? One component is 0 and one is not. Which one is 0? Yeah, VFY is 0. We don't know VFX. Well, we do if we're at a cocktail party and just chatting with people trying to act smart, but for filling out this stuff, don't. So it is true that the velocity at every instant would be 3.9, the x component, but don't put it down here or it'll just confuse things. It'll make it look like equations are going to work, that when you fill out the stuff, it's just going to say 0 equals 0 and it won't help. Okay, so what can we figure out? I suppose we can figure out PIY from this equation. 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So that says negative 19.62 times the quantity PFY minus 1.96 is equal to 0 squared minus 6.76 squared. I'll divide both sides by 19.62. And you get that PFY minus 1.96 is equal to 2.33. And now add 1.96 to both sides. And PFY is equal to 4.29. So that's half of what we need. Now we need to figure out the x component of the final position. There's no way to do that. So no equation works for PFX. So again, we need to start by finding time final. And so the equation that I'm going to use to find time final is VFY is equal to VIY plus AYTF. So 0 is equal to 6.76 minus 9.81 TF. And so 9.81 TF is equal to 6.76. Divide both sides by 9.81. And you get TF is about 0.69 seconds. Does it make sense that TF is smaller for part B than it was for part A? Yeah, because the ball has to get to the highest point, and then time keeps going as it goes down and gets to the basket. Okay? And now we can use this equation, PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 3.9 times 0.69 plus 0. And so PFX is 2.69 meters. Okay, so now we have the X and Y components of P final. So that's 2.69, 4.29. And so the displacement is 2.69, 4.29 minus 0, 1.96. And so that's 2.69 2.33 meters. And here's the meaning of that displacement vector. So the ball's shot from here. The highest point is here. And so the displacement vector is the vector that goes from where it's released to that highest point. And you can see it makes sense. I mean, this is obviously just a very rough sketch, but you can see that vector is, it's sort of plausible that that vector would come out to be, where is it? You know, about the same x horizontal component as vertical component. You know, that vector is in the first quadrant, sort of right at about 45 degrees. So, anybody have any questions about that problem? Okay, any other homework questions you'd like me to go over? Okay, so now we're getting back to particle kinetics. And I said last time that we're going to break up forces into categories like this. First is the weight force. And we know that that acts straight down, and it's equal to the mass of the object times the acceleration of gravity in free fall. And then second, the only other category of forces are contact forces. So these are forces applied by objects touching or in contact with the chosen body. And there are three types of these forces that we're going to deal with. So the first one is a pushing force. The second one is a pulling force. And you can always imagine that being applied by a string or a cable. So even if there's no cable, we're going to think of it as if there is a cable. And then the third one is a friction force. Okay? And so now we're going to be spending a little bit of time just going through these. We've already talked about how to know what the weight force is. Now we're going to, be talking about identifying and representing pushing, pulling, and friction forces. You can see that, you can imagine that in complicated problems, this can start to get sort of messy. And a lot of times it's really helpful to have a visual thing that helps you keep these forces, keep track of these forces in your head. And for us, that is going to be called a free body diagram. So to keep track of the forces, we're going to always draw a free body diagram. And when I talk about that, I'm just going to abbreviate it FBD, free body diagram. And the phrase free body diagram comes from the fact that we're going to choose the body that we're going to do the analysis for. And then we're going to take everything else out of the problem. Nothing else is going to exist in our diagram except the outline of the body, and then anything that's touching the body, it's not going to be represented as a drawing or anything. It's just going to be represented as forces. So that's what the free part comes from. Our body's going to be there, and everything else will be gone and just replaced by the forces it applies. Okay. So I'm going to expect that you're going to draw a free body diagram every time you use Newton's second law. And here are the steps for drawing a free body diagram. First, draw a closed outline of the chosen body. with no external objects and no internal details. Okay, so for example, say that you're doing something that involves this guy standing on the ground. That's supposed to be grass. So when you draw your free body diagram, if you're isolating the person, you draw something like this. You don't have to be artistic about it or anything, but it should be clear what is inside your boundary and what's outside your boundary. That's the important thing that we're showing here. What's in the in club and what's excluded. Okay. So some examples of things that don't that you shouldn't do. Don't do this because it's not a closed outline. Don't do this because he's not happy. No, just kidding. Because that has internal details. And don't do this because the ground and the grass are external objects. And it just gets confusing. Like, what am I, like, now do I have to worry about the forces that are being applied to the grass? That's the kind of ambiguity that we're trying to clear up with this diagram. Okay? So after you've drawn this outline, draw a downward arrow representing the weight force. And label this downward arrow either mg is fine to write, or with the numeric weight. So like, for example, if you know that this person's mass is 50 kilograms, 50 times 9.81 is 490.5. So you could label it mg or you could label it 490.5. And so at this point, your free body diagram looks like this. So you have the outline. You have a downward force like that. And I didn't give his mass, so I'll just call it mg. And then third, at each point where the surroundings make contact with the boundary, draw an arrow in the direction of the contact force. And then label that arrow with a value if you happen to know what that force is. Usually you won't. Or with a variable representing the magnitude of that force. Okay, so in this case, here's the outline. There's the weight force. And if we look back at the picture, where do the surroundings make contact with the boundary? Yeah, right. The ground contacts the feet. And so we have to represent that somehow. Don't worry about how you know this yet. This is what we're going to get into, but that's an upward force that the ground applies to the person. I don't know what that is, so I'm going to give it a variable name, and I'll call it N. And then that's a complete free body diagram of what we're doing. This is a pretty simple, this would be a pretty simple problem. So you might think like, oh, well, why do I need to draw this picture to keep track of two forces? But the thing is, problems can get really complicated. And so it's a good habit to get into while we're doing simple problems that'll carry you over to the more complicated ones. And here's the thing I want you to notice about free body diagrams. The free body diagram tells you everything that goes into the left side of Newton's second law. So the free body diagram tells you everything about the left side of Newton's second law. So Newton's second law says add up all the forces acting on the chosen body. That's equal to the body's mass times acceleration. Well, the net force, this is just the sum of all the forces. So you go to your free body diagram. You represent each one of these as a force vector. And once you've done that, you know you're done with the left side, and all you have to worry about is the mass and the acceleration on the right side. Okay, so now we're getting, so now the question is, how did I know that the force applied to the feet by the ground had an upward direction? That's the one thing that I didn't really explain. And so now that's what we're going to get into. For these different types of contact forces, what's the direction of the arrow that you draw? Okay. So now we need to know the directions of contact force vectors. There are three types of contact forces that I mentioned at the start: pushing, pulling, and friction. And we're just going to go through those one by one and talk about how you know what direction those are acting. Okay, so I'm going to start with pushing forces. So a pushing force you can think of as a force that prevents the surrounding objects from invading actually, let me, blah, blah, blah. Let me word this the other way. So think of this as a force that prevents the chosen object from invading the space of the surroundings, invading the space of surrounding objects. Like if I ran at the wall would apply a very sudden force to me that kept me from merging, blending through the wall. Okay, that's a pushing force. So examples of pushing forces are like if you have two rolling carts in contact with each other. And let's say they're being pushed together by these two forces here. Let's say this is cart 1 and this is cart 2. Then where is pushing happening? There's pushing happening between the ground and the wheels of each cart. So there's a pushing force there. There's another pushing contact there. And there's a pushing contact here. Okay. Both of the objects are defending their space. If that force wasn't there, they would cross boundaries. Okay. So when you have a pushing contact like this, or a pushing force direction, the force is always perpendicular to the surface of contact. Toward the chosen body. Okay, so let's think about how these, the directions that these forces would take in these two bodies. So I'll start with a free body diagram of body 1. So there's the closed outline of body 1. And there's a weight force acting down. I'll call that M1G. I didn't give the mass of this thing. So there's the weight force. Then around the boundary, we know that 50 Newton force is applied to the boundary. So I'll just put that in. And now let's think about the pushing forces. The ground is pushing on the wheels. So let's think about this direction rule. The surface of contact is like this. The force has to be perpendicular to that, which means either up or down. And then it's toward the body, so up. And I'll call that N. and for normal force. That's a pretty common variable name for pushing forces. And then I'll go over to where the two carts are in contact with each other. There's a pushing contact there. The surface of contact is like that vertical wall. And so the force is perpendicular to that, toward the chosen body. And I'll give that a variable name too. I'll call that R for reaction force. That's another common name for pushing forces. And let me draw the free body diagram of the other one too. Okay, so there's a weight force down. That's whatever the mass is times 9.81. There's 100 Newton force acting on the boundary of the second one. So that's over here. But notice that 100 didn't appear on body 1 and that 50 didn't appear on body 2. We're only putting in the stuff happening on the boundary of that chosen body, okay? And now the two pushing forces. Well, there's a pushing force to the wheels from the ground. That's perpendicular to the surface toward the chosen body. And that doesn't have the same value as the N above, so I'm going to give it its own name. I'll just call it N2 in this case, just to give it a different variable name. And then over here, there's also a pushing contact from body 1. That's perpendicular to the surface toward the chosen body, so this way. And I'm going to call this one R. And the next thing I want to say is, what about this? So notice that these two pushing forces are, the opposite directions, but I didn't call these N's the same thing. Why am I calling these R's the same thing? And so this is an important fact about pushing forces. When two objects push on each other, when two objects push on each other, the force applied to one has the same magnitude as the force applied to the other one. Okay, this is a surprising fact. This is connected to something called Newton's third law that we'll talk about more pretty soon. But it's surprising, but we'll see that it's always true. And so what that means is if you go from a free body diagram of one of the two bodies to a free body diagram of the other one, use the same variable for that contact force. Use the same variable name. Okay, so there was only one place where we had to deal with that. There was only one place where, so I did these two free body diagrams, right? Body 1 and body 2. And there's only one place where body 1 and body 2 are applying forces to each other. At that force, you're going to use the same variable in one free body diagram as you do for the other one. Okay, any questions about that yet? All right, so the next thing and the last one we're going to do today, we'll do friction next time, but today we're going to talk about pulling forces. And we're going to always think about these as being applied by cables or strings. Even if they don't have to, you could replace the contact with a cable or string if it's a pulling force. And so you can always identify a pulling force if the contact could be replaced by a cable or a string without changing what happens in the problem. Okay, so I said that a pushing force is keeping the chosen object from invading the space of the surroundings. A pulling force is when the surroundings are keeping the chosen object from escaping, okay? So for example, let's think about two objects, two rolling carts that are connected by a bar, a cable, or something. This is body 1, body 2, and let's say that there's a force applied this way of 300 newtons. Well, if you apply that 300 Newton force to the right, it's going to make that cart 2 roll to the right, okay? And what that cable between them does is keep those two things from separating. It's making cart 1 stay with cart 2, okay? So that's a pulling force. And so this and this are pulling forces. This and this are pushing forces. And the direction of the pulling force is parallel to the cable away from the chosen body. So a pushing force is toward the chosen body, a pulling force is away from the chosen body. okay? So let me draw free body diagrams for both of these. For body 1, we have a weight force of mass of body 1 times g. Then we have a pushing force that the ground applies to the wheels. So that's perpendicular to the surface toward the chosen body. I guess I'll call that N1. And then the only other place the surroundings contact the boundary are at that cable. And the rules say that force is parallel to the cable, away from the chosen body, and I'll give it the name T for tension. And then a free body diagram of the second body. We have a weight force of the mass of body 2 times g. We have a pushing force from the ground. I'll call that N2. We have the 300 Newton force that's just given to us, so I'm just going to put that in here. But notice that it only acts on body 2. It doesn't act on the boundary of body 1. And then the last thing is we have a pulling force, and the rules say the force is parallel to the cable, away from the chosen body. And I'm going to give that the same variable name that I gave the other one. Okay, so with pushing forces, I said there's this important thing that happens when you have two bodies in contact with each other. There's something like that with pulling forces that explains why these two variables are the same. So important. If the same cable pulls on two different bodies, the force magnitude is the same on both. And one thing that we're going to see a bunch is this is even true if that cable passes over through pulleys between the two ends of it, okay? So this is even true when that cable passes through pulleys. Okay, so let's do an example problem where we're just doing free body diagrams of sort of a complicated setup. So let's say that we have an incline And there's a rolling cart on this incline. And let's say this has a mass of 10 kilograms. And then a cable that's attached to this cart goes over a pulley, and then it's connected to a hanging mass that has a mass of 5 kilograms. And let's say that there's some external force applied here of 10 newtons. So we're going to draw free body diagrams of both masses. Okay, I guess I'll start with the 5 kilogram. So here's an outline of the boundary. There's a weight force acting down that's equal to the mass times 9.81. So 5 times 9.81 is 49.05 newtons. Then we're told that there's a 10 Newton force acting down. And then the only other force is applied by a cable, so we know that's a pulling force. And that force is parallel to the cable, away from the body, and I'll give it the name T. Any questions about that? And then a free body diagram of the 10 kilogram. So there's the outline. There's a weight force that acts straight down. That's 10 times 9.81, so 98.1 newtons. Now there's a pushing force from the incline. That force is perpendicular to the surface toward the chosen body. So that's going to be at an angle like this. And I'll give that the name N. And then the only thing left, because you can just go around the boundary and look for contacts, there's a cable that makes contact over here. That's a pulling force, so it's parallel to the cable, so at an angle, away from the body. It's the same cable as this one, so I have to give it the same force name T. Even though they're in different directions, they have the same magnitudes. Okay? Any questions about that? Okay. Let's do one more example, and I'll give you a few minutes to do it to try to make sense out of this stuff. So let's say we have an incline going this way. And let's say we have 2 blocks, carts in contact. And let's say there's a 50 Newton force here. Let's say this one is 2 kilograms and this one is 5 kilograms. And we want to draw free body diagrams of each one of these. Okay, so take a couple minutes and first do the free body diagram of the 2 kilogram cart. Okay, so for the first one, this 2 kilogram, so there's the outline. There's a weight force down that's equal to 2 times 9.81, so that's 19.62. There's the 50 Newton force that's given. There's a pushing contact from the incline to the wheels, so that's perpendicular to the incline toward the chosen body, and I'll call that N1. You might have called that something different, but it's fine. It's just a variable name. And then the last thing is there's a pushing force from the 5 kilogram. So that's perpendicular to this surface toward the chosen body, and I'll call that R. And now take a couple minutes and see if you can draw the free body diagram for the 5 kilogram cart. Okay, so here's the outline. The weight force is straight down, and that's 5 times 9.81, so 49.05 newtons. Then there's a pushing force from the ramp, so that's perpendicular to the ramp toward the chosen body, and I'll give that a name. Just be sure that that variable name is different than the first one. I guess I'll call that N2. Those are different variables. They have different magnitudes. And then go around the boundary until you get to anywhere else there's contact. This is being pushed on by the 2 kilogram. And so the rules say perpendicular to the surface, toward the chosen body. And since this one is a contact between these two bodies, it has to have the same variable name that it did over here. So even though those two, this and this, are in opposite directions, they have the same magnitude, the same variable name. Okay? So now, the assignment I'm going to give you is just stuff like this. But the key fact about this is once you have these in here, now all you have to do is represent these as vector components to put them into Newton's second law. And you've already had practice doing that kind of stuff. So we're pretty close to being able to put this stuff into Newton's second law and actually to start calculating like what these forces are or what the acceleration of the thing is. Okay? Okay, well, some of you have lab, and then the rest of you, happy spring break. Woo! See you in Daytona.